Little League. Baseball is a favored recreation throughout the Cape Kennedy area. There's a nearby game underway almost every evening of the spring and summer. Here, midway between Patrick Air Force Base, headquarters for the Air Force Eastern Test Range, and Cape Kennedy, America's best-known launch site, the evening traffic flow is normal. As is customary, quite a number of families have succumbed to the lure of gourmet dining in one of many fine restaurants in the area. Several couples, awaiting their turn to dine, are enjoying a few moments in the lounge, aware that a launch is scheduled for this evening.
Coming up on T-minus 30 seconds and counting on my mark. Mark, T-minus 30 seconds and counting.
Stand by for terminal count.
Stand by for terminal count.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition confirmed. Ignition.
Roger wire.
TM confirms all engines go.
Liftoff.
Roger wire. Understand liftoff. Roger TM. All engines go.
TM shows program downrange.
Roger TM.
VPs are green.
Wire green.
Roger wire. Roger VP.
Picking up excessive pitch on TM.
Roger TM. Excessive pitch.
Radar on the nose. TM jet solid.
Roger TM. Understand jet. IP is left of nominal, about 10 seconds slow at this time, moving downrange. IP is starting to move back towards the Cape.
TM confirms missile erratic, excessive pitch.
Roger, spinning arm, sending destruct.
The mission of the Air Force Eastern Test Range is to provide the facilities for launching this nation's space vehicles and to provide for the protection of lives and property from errant missiles. Even though today's boosters are reaching high levels of reliability, as commander of the Air Force Eastern Test Range, I must still prepare for a small percentage of failures. From the very beginning, one of our principal concerns has been range safety. The first launch from Cape Kennedy, then called Cape Canaveral, was July 24, 1950. It was called Bumper, a German V-2 rocket with a WAC Corporal second stage. Support equipment was primitive and makeshift. But the means for stopping an errant missile was not left unattended. A command-controlled strut package was provided so that a radio signal sent from the blockhouse would stop the missile in flight. The Army-sponsored Bumper test was a complete success. Today, because of the enormous potential of modern boosters, there is considerably more to the business of safety. To show how range safety fulfills its responsibilities, let us follow the preparation that goes into the launch of the Air Force's most powerful space vehicle.
This is the Titan 3C, the 14th to be launched from the Air Force Eastern Test Range. It stands 128 feet high and develops 2.5 million pounds of thrust at liftoff. Its payload, 2 Vela nuclear detection satellites, to be placed into separate, precise orbits by the highly sophisticated booster system. But the story doesn't begin here. Planning for the flight began about a year before the launch. Once the decision was made to launch the Titan, the launching agency, the 6555th Aerospace Test Group, brought details of the mission and the proposed trajectory to range safety. Under the chairmanship of the Director of Range Operations, Range Safety meets with members of the range support agencies and the Test Group Titan project officers. In order to receive flight approval, certain stringent range safety requirements would have to be met. The space vehicle, for example, would have to accomplish its mission within specified launch azimuths. The boosters would have to carry approved electronic decoders to receive the range safety command for destruct should the need arise. Radar transponders on the missile would have to meet precise specifications to ensure positive tracking throughout the flight. After reaching initial agreement as to what is expected, mathematicians start the intricate work of deciphering trajectory information. Programmed into the IBM 36065 and 7094 computers are basic data about weight, thrust, burn times, stage separation, and other factors. Eventually, questions concerning range safety will be answered. For instance, on the azimuth and trajectory requested, will a spent stage impact in a Caribbean island, a distant shipping lane, or in Africa? The answers to such questions are critical considerations in establishing final approval of the flight. While the Range Safety Office and the test group are resolving the details of launch approval, assembly of the space booster begins. The stages of the core vehicle arrive by cargo plane. Offloaded on special transporters, they are carefully moved to the assembly area. Segments of the rocket motor boosters arrive by rail and are readied for the assembly procedures. Inside the vertical integration building, the liquid-fueled three-stage core vehicle is erected directly on its mobile launcher. The multi-burn third stage, called the tran-stage, serves as a switch engine in space and is what makes this booster system so versatile. Its stop and restart capability makes it possible to place as many as 8 payloads in different space orbits. From the vertical integration building, the fully assembled core vehicle is transported by 2 diesel locomotives to the solid motor assembly building, the last assembly point before the launch vehicle reaches the pad. Here, solid rocket motor segments, each 10 feet in diameter and 10 feet high, are in process of assembly prior to being attached to the core vehicle. The completed booster leaves the solid motor assembly building on the final leg of its journey to the launch site. The 2 solid boosters, 85 feet high, carry the core vehicle and payload to an altitude of nearly 25 miles before they burn out and are jettisoned. At the spin test facility, while the launch vehicle is being prepared, each of the 2 Vela satellites are dynamically balanced and tested for structural integrity. This is the final spacecraft checkout before transport to the launch pad, where it will join the waiting Titan 3C. With the Titan at the launch pedestal, pad safety prepares for the more hazardous of pre-launch operations. Final checkout of the redundant command-destruct system begins. In addition to explosive primacord in the solid propellant stages, wafer charges are mounted within the liquid propellant core vehicle between the fuel and oxidizer tanks. These explosives are attached to pyrotechnic squibs, the key link in the destruct system. Should the range safety officer need to destroy the space vehicle, the explosives will be fired by the squibs when either one of the 2 command control receivers receives the destruct signal. With the ordnance installation completed, the command destruct system is go. Another, and potentially the most catastrophic of pre-launch operations, is the fueling of the vehicle. Nitrogen tetroxide is the oxidizer, Aerosine 50 the fuel. The Titan 3C carries 300,000 pounds of these hypergolics, by far the largest amount of this type of propellants loaded by any United States missile. They are hazardous not only because of their incendiary and explosive potential, but because each is highly toxic to man. Protective clothing worn by handlers insulates them from splashes or fumes. As demonstrated in the laboratory, the propellants have the additional advantages of being shock-proof and storable, as well as yielding a high specific thrust. That is, high thrust per pound of propellant per second, and most significantly, they ignite on contact. In the vertical integration building, an important coordination effort is near completion. From the onset of launch preparations, the Range Safety Officer, or RSO, has been learning every aspect of the vehicle, its components, its operations, its systems, and its various idiosyncrasies. In addition, he has gone through repeated procedures drills with computerized simulations of liftoff and flight. By launch time, he will have a comprehensive knowledge of the Titan 3C, as well as quick response reactions to flight variables which might occur. After flight trajectories have been finalized and launch conditions approved, the RSO discusses with the mathematicians of the Flight Analysis Branch the preparation of the range safety destruct charts. Utilizing the answers that were compiled by the larger computers, smaller computers develop criteria upon which the range safety officer can make his decisions. On various overlays, destruct lines are drawn. These lines are based on expected winds at launch time, velocity imparted to pieces by explosion of the destruct charge, missile velocity, maximum turning rates, survivability and ballistic coefficients of re-entering bodies, and the range safety officer's reaction times. The results are precisely calculated boundaries that protect land masses such as the United States mainland, the Caribbean island chain, South America, Europe, and Africa. On the charts, two kinds of trajectory information are plotted: the actual vehicle position in space and the instantaneous predicted impact point on the surface of the Earth. Should the missile veer off course and the predicted impact point reach a flight termination line, the message to stop the flight must be sent by the range safety officer. The CDC 3600 computer is used to overcome the complex mathematical problem of calculating this trajectory information and presenting it to the range safety officer instantly. The most critical part of the launch in terms of safety is in the launch area, because approximately 90% of all missile failures occur soon after liftoff. During this period, the RSO relies on several charts, such as close-in impact prediction destruct lines. Immediately after liftoff, the difference between a safe nominal missile and a catastrophe is just a fraction in terms of time and distance. Another important display for the RSO is the vertical plane, or VP chart. This provides him with a different type of destruct criteria during the critical moments of early flight. The responsibility of the RSO at this time is made even more burdensome because he must not only solve the problem of protection, but must also allow the missile the maximum permissible opportunity to fly and achieve its mission. A chart of present position deviation lines is a third source of information for the RSO. The sensors that support the range safety officer are varied and numerous. Television provides both flight line and program view of missile flight. Not the least important is the wire sky screen, which, despite its simplicity, provides valuable information in the first few seconds of flight before radars can positively acquire. 3 radars are located on the mainland, and 5 others downrange as far as the island of Antigua. Typical of range safety radars, designed specifically for missiles, is the Patrick MIPR, Missile Precision Instrumentation Radar, with a 29-foot antenna which can track with precision a space vehicle 60,000 miles in space. Downrange, as well as on the mainland, telemetry receivers provide such data as thrust chamber pressures, yaw, pitch, and roll rates, destruct receiver sensitivity, and staging events. Telemetry antennas at the Eastern Test Range are among the most sensitive in the world. This 85-foot antenna can receive telemetry signals from space vehicles over 4 million miles away. As launch time approaches, with all systems checked out and the missile fully fueled, the Titan 3C is ready for flight. In the vertical integration building about 2 miles from the pad, launch operations are being conducted from the Launch Control Center. From here, the orderly countdown of the missile's pre-launch tasks is directed by the test conductor. Every detail of the launch vehicle systems, the payload, and continuity of all electrical connections are confirmed as operational during the long countdown. At the Range Control Center, the RSO conducts the countdown that establishes the readiness of the range to support the launch. The Range Safety Officer is the direct representative of the commander during the launch phase. He is therefore responsible to ensure that all launch operations concerning safety have been accomplished prior to liftoff, or he will not permit the launch to take place. All key areas are incorporated into his countdown, and through a series of questions and responses, he receives, through his vast communications net, the go condition of the entire range. The RSO makes an early call to sea surveillance. Concern now is for those who may have strayed into the ocean areas immediately below the missile's flight path. Helicopters, equipped with radios and bullhorns, patrol out to 20 miles. Up to the 3-mile limit, Coast Guard cutters intercept vessels which may have entered the danger area and direct them to a safer course. From radars as well as these visual sources, information about intruding ships is received and locations plotted. The pad safety supervisor responding to the RSO's call reports on the state of the missile destruct system and that the land launch danger area is clear. This means that all people have been evacuated and that the impact convoy is standing by, ready to control the area in case of disaster. The RSO punches up command control. He reports on the status of all command antennas, the high-power command system, radiating and ready to support, the low-power command system, standing by, condition go, and all downrange command antennas, such as at Grand Bahama, checked out and ready. Frequency control and analysis reports directly to the RSO. He confirms no radio interference on command frequency. FCA is go. CADAC, or Central Analog Data Distribution and Control, immediately behind the RSO, confirms the plotting boards are checked and calibrated, and the computer theoretical trajectory correlates. The Range Safety Officer rings the SRO. The Superintendent of Range Operations declares all range safety instrumentation, such as radars and telemetry, are operational and go. He confirms critical items, and that he will hold, meaning prevent launch, should any range safety mandatory instrumentation drop out prior to liftoff. This could include a signal transponder, a critical radar, or the impact predictor. During the last few minutes, the launch test conductor at the vertical integration building receives the word that all missile systems are go and the final countdown is underway. Every effort has been made to make this a perfect launch. In the range control center, the range safety officer is completing the range support countdown. He is ready to contend with the ever-present possibility that the launch might be less than perfect.
This is the RSO for a final communications check. Parish 3.
Parish 3.
Parish 7.
7.
Parish 91.
91.
Wire.
Wire.
Radar.
Radar.
Telemetry.
TM.
T-minus 50 seconds.
SRO.
What's the range instrumentation status, please?
018 is skin only, committing at T plus 18 seconds. All other instrumentation is go.
Roger, copy 018
40
status.
seconds.
Unless you have a further change, you have a final clearance to launch.
Roger, understand. Final clearance to launch.
Okay, you get enable, local disable. Roger that. Command
T-minus
carrier
30
covers
seconds.
off. Switch covers up. We're at T-minus 25 seconds and counting.
TM reports AGC's are
T-minus 20 seconds.
Roger, TM. Understand AGC's green.
T-minus
T-minus
15
15
seconds.
seconds and counting.
Stand by for terminal count.
Okay, Tom, stand by first motion.
10,
Roger that.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition confirmed.
Wire ignition.
Roger, wire.
Wire liftoff.
Roger, wire.
TM has changed for pressure.
Roger, TM.
Plus 10 seconds. Mark.
Climbing the wire.
Roger, wire.
Wire is green.
Roger, wire. The VPs are moving up.
Right, VP screen, you got first motion.
Plus 20 seconds. Mark.
Wire is green.
Roger, wire. Understand green.
TM green.
Roger, TM.
Wire programming downrange.
Roger, wire.
Plus
TM
30
confirms
seconds.
we're going
Mark.
downrange.
Plus
VPs are green,
40
and I'm
seconds.
picking up an alternate
Mark.
IP on the nominal. I have an IP on the primary, pass 1. Primary IP looks good. It's right on the
Plus
nominal.
50
At this time,
seconds.
we're plotting
Mark.
116 on the beacon.
TM green.
Roger, TM. Understand green. The VPs
Plus
are
60
good.
seconds.
Paralleling the nominal on
Mark.
maybe a 16th of an inch. We're about to go off the board in maybe another 5 seconds or so. We're picking up pass 2 now on the primary
Plus
IP. It looks
70
like we have
seconds.
1918
Mark.
beacon.
Roger, I got the 116 beacon and right on the nominal, and radar's on, going slightly high on board 1.
Roger that.
Okay, now we're 1 second off, 1 second slow.
That sounds good.
Carrier on station 3.
Plus
Roger,
100
station 3,
seconds.
carrier on.
Mark.
TM, we're coming up on stage 1 ignition.
Roger, TM.
Plus 110 seconds. Mark.
Stage 1 ignition.
Roger, TM.
Okay, I got the 018 beacon right on the nominal. My
Plus
board is
120
showing high on the
seconds.
radar, but
Mark.
my second board's showing right on. I believe I've got a bias in the first board.
Roger.
Good.
We should have SRM jettison.
Plus 130 seconds. Mark.
Jettison, solid rocket motor cases.
Roger that. We have 1918 beacon
Plus
on
140
the
seconds.
second pass of the
Mark.
primary IP. Pass 3 is moving out now. It's right on the nominal. Everything looks good.
Radar green, IP, alternate IP, nominal.
Plus 250
Looks good.
seconds.
We have
Mark.
about 10 seconds to stage 1 separation.
Stage
Plus
1 is counting off.
260 seconds.
Roger, TM.
Mark.
Stage 1 separation. Stage 2 ignition.
Roger, TM.
Carrier on station 91.
Roger, 91.
Station 7 carrier off.
Roger, 7.
Plus
We're at
460
460.
seconds.
Mark.
Mark.
IP's moving out now.
Stage 2 is cut off.
Roger, TM.
Plus 470
right on
seconds.
down.
Looks like we're going to make an orbit. We're through the gate.
The importance we place on safety is measured by the efforts underlined in this picture. During 20 years of missile testing at the Eastern Test Range, we have supported over 1,800 major launches without a single casualty. This, I believe, we can attribute to our stringent range safety procedure. The knowledge gained through our increasing experience will mean a future with even fewer missile malfunctions. Notwithstanding, the Air Force Eastern Test Range is committed to provide continued evaluation of missile performance, with range safety serving as a shield against potential disaster.